Good morning, everyone. I'm Dr. Imane. I'm a lecturer and a researcher at the University of Science and Technology, Houari Boumediene, Faculty of Mechanical and Process Engineering. So it's a pleasure to be present with you today. I would like to thank all the organization and scientific committee for this important and interesting opportunity. Now let's start my presentation entitled Use of an Eco-Friendly Biosorbent for the Treatment of Water Polluted by Methylrosaniline Chloride. So we have experimentation and modeling. Water pollution has become a real threat in recent years. As industrial activity increases, wastewater needs to be treated continuously and effectively so to prevent ecosystems from contaminations. Research in this area is still ongoing, creating new materials, processes, and techniques for treating water. Comparable to traditional methods, newer techniques like adsorption have shown their effectiveness in removing various metal and organic pollutants from wastewater. The materials used, such as active carbon and natural biosorbents, have demonstrated promising decontamination results, especially the biosorbents made from agricultural and food waste. This study aims to determine the effectiveness of a biosorbent made from orange peel in removing the crystal violet dye from contaminated water through continuous adsorption. This work presents the results along with a modeling of the breakthrough curve obtained during the adsorption of crystal violet dye under various operating conditions. We start this part with the preparation of the bioadsorbent or the biosorbent. So the biosorbent used in this study was prepared from the orange peel. So the peels were collected, thoroughly washed with distilled water and dried in an oven at 105 degrees C for 24 hours. After drying, the peels were finally ground to a homogeneous powder ready for use as a biosorbent or adsorbent biomass. The dye studied in this work is crystal violet, so whose main characteristics are presented in the table below. We have the denomination, chemical name, group or family, molecular mass, chemical structure, and lambda max about the absorption. Okay, so we pass now to the next slide. To explain bioadsorbent performance, its efficiency is measured by the percentage of initially dissolved solute retained. So the percentage of the dye removal R in percent has been calculated using the following equation, where C0 and Ce are the initial and equilibrium concentration of the dye in solubility, and the results were modeled using the following, the Boart-Adams model. So we have the equation and the plot. With C0, the initial solubility concentration, Ct outlet concentration of dye, T the time in minutes, Kib Boart-Adams kinetic constant, and 0 the maximum adsorption volume capacity, Z bed height in centimeter, F the linear velocity of mobile phase. We pass now to the experimental data. So we have the table below presents the operating parameters and the equilibrium dye removal rate at the saturation. We have the flow that was 20 milliliter per minute Adsorbent weight 4 grams, bed height 3 centimeters, and linear speed f, it was 4.07 centimeter per minute. We pass now to the equilibrium dye removal rate due to the saturation in percent. We have for the first concentration of crystal violet 40 milligram per liter, so it was 61%. For the second concentration, we found that the R in percent was 71.3, and finally for 60 milligram per liter, we found that the R in percent was 90.63%. So by following the adsorption as a function of time enabled us to measure the concentration at time and then plot the following breakthrough curves representing the variation of C per C0 as function of time. We have the three plots, so for the concentration of 40, 60, 50 and 60 milligram per liter. So as we can see, it's clear that the three graphs illustrate how the C per C0 ratio changes over the time for varying starting concentration, which is typically of fixed column adsorption investigation. These breakthrough curves are crucial for evaluating an adsorbent's performance in dynamic environment or dynamic mode. So the gradual increase in the C per C0 ratio over time suggests that the biomaterial is gradually becoming saturated. So breakthrough appears to happen more quickly and fastly at higher concentration, which is an unexpected finding given the scientific literature on dynamic mode adsorption. So here we found that accelerated saturation of the active sites explain this observation. Adsorption sites saturate more quickly and fastly at high concentration. A multi-stage adsorption process is suggested by the curve's typical sigmoidal shape. The phase 1, so we have fast adsorption at external locations that are easily accessible. Then we have the second phase, so it's a division of interparticle into the pores of biomaterial, and finally adsorption and desorption. We can say that they are in balance during the saturation phase. So now we pass to the part 2, modeling results using the Boart-Adams model. So we have the figure to represent adsorption modeling using the Boart-Adams model for the concentration 40, 60 and 50 milligram per liter. So by modeling the results using the Boart-Adams model, we have found the next values of the different parameters. So we start with the parameters in the case of the dye concentration of 40 milligram per liter. So for the KAB it was 0.0021, and there we found that it is 1453, and the correlation factor we found that it's equal to 0.719. And we pass now to the second concentration of 50 milligram per liter. So for the KAB it was 0.0014. So then we will pass to the N0. We found that the value of the N0 in this case it is 2432, and finally the correlation factor we found that it's equal to 0.579, and finally the last concentration of 60 milligram per liter. So here we found that the KAB equal to 0.000 81, and for the N0 we found that it's equal to 5226, and finally the factor of correlation, we found that it's in the order of 0.673. As a conclusion, all of the study's finding can be summed up as following. Adsorption is faster, but total capacity is lower at low concentrations. The volume capacity increases at high concentrations, but the unit adsorption rate falls, indicating a more gradual saturation of the bed. And finally, we have shown that the dynamic capacity of the biomaterial can be estimated with the help of the Boart-Adams model, and the potential of this bioadsorbent to treat effluent at varying concentrations is confirmed by these dynamic adsorption results on our biomaterial. So I would like to thank you, and I wish that it was interesting presentation. Thank you.